Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with MetaGeek. Today's host is Joel Crane. He is their technical trainer. He'll be presenting today, and if anyone has any questions, please feel free to submit them in the question box, and Joel will answer them at the end of today's presentation. Thank you all for being with us. I am finished. Go ahead, and the floor is now yours.
Great, thanks, Julie. Welcome to Visual Packet Analysis with IPA and AirPCAP NX. In this video, or in this webinar rather, we're going to take a look at how you can perform packet analysis in a visual way. I'm sure most of us are familiar with a typical packet analysis tool like Wireshark, but I'm going to show you a unique way that IPA handles packet analysis and all that stuff. So it should be a lot of fun. My name's Joel. I'm the technical trainer here at MetaGeek. We're a small company based out of Boise, Idaho. We're a team of about 20 people, and we like to make easy-to-use wireless troubleshooting tools. So if you have any questions about MetaGeek stuff, be sure to contact Microcom. They'd be more than happy to answer any questions that you have about any products that you see in this webinar. So the first thing I'd like to do when I present on packet analysis, I always like to start out with the basics of Wi-Fi, the building blocks of Wi-Fi. The first thing I like to cover is how Wi-Fi is the half-duplex nature of Wi-Fi. Now, this is a pretty simple concept, but we're going to build on this as time goes on. We're going to start with the simple stuff and work our way up from there. So let's go ahead and take a look at this concept. Now, Wi-Fi is half-duplex. Now, if you're familiar with Ethernet, then you'll know that Ethernet is full duplex. Basically, with an Ethernet cable, we can send traffic in two directions at the same time because Ethernet is full duplex. Wi-Fi, on the other hand, is half duplex, meaning that we can only send traffic in one direction at a time. Wi-Fi is a lot like a human conversation. If you're talking and you say something and your friend says something at the exact same time, you can't understand each other. You'll both basically cancel each other out, and you can't understand what your friend is trying to say, and your friend can't understand what you're trying to say. Wi-Fi is the exact same way. If we've got two Wi-Fi devices that are on the same channel, like maybe an access point and a client device like a laptop, if they both try to transmit at the same time, they're going to basically cancel each other out. They're going to interrupt each other's signals, and they're not going to be able to understand each other. Only one Wi-Fi device can talk on a channel at a time, and that's a rule that we're going to build on throughout the course of this webinar. So how do devices talk? How do devices exchange information? Well, let's say that we've got an access point and we've got a client device, and the access point has some data that it needs to send to the client device. The first thing that the access point is going to do is it's going to perform what's called a clear channel assessment. It's going to basically listen to the channel to see if there's anything talking on the channel. And if it hears that there's nothing talking there and that the channel is clear, it will use that opportunity to transmit the data to the laptop. So it'll transmit the data to the laptop, and now the laptop is going to basically pull out the magnifying glass. It's going to take a look at that data that it just received and make sure that it can understand it. And if it can understand it, it'll go, yep, check, I understood the data, and it will reply with an acknowledgement. So it's a constant process of sending data and then acknowledging that data. And remember, it doesn't matter which direction the traffic is flowing, and we could basically swap these arrows in the opposite direction, and the process is going to work exactly the same. It doesn't matter which device is transmitting. If the laptop sends some data to the access point will always reply with an acknowledgement to confirm that it received the data. But there's a couple of things that can go wrong here. Let's say that the access point transmits the data, but the data just doesn't quite make it through to the laptop. Maybe the data gets garbled along the way, or maybe something else started talking in the middle of the transmission and interrupted it. For whatever reason, the laptop received garbled data or bad data that it can't understand. It's when it pulls out the magnifying glass to take a look at that data, it's not going to understand the data, so it's not going to send that acknowledgement. It's not going to say, yep, I received the data, because it did not receive the data. So the access point's going to start going, okay, well, I never heard the acknowledgement from the access point, so I must not have received the data. So it's going to transmit it again and again and again and again. It's going to keep retransmitting that data until finally the data makes it through to the laptop, and the laptop can go, yep, check, I understood the data, and it can reply with an acknowledgement. I like to think that Wi-Fi is a lot like my kids at home. I've got 3 daughters at home, and the youngest is 3. And so she's full of questions right now. She has many, many questions about all kinds of things. And they're very, very simple questions. And if I'm sitting on the couch reading a book or something like that, and she asks me a question, if I don't give her some kind of acknowledgement, if I don't answer her question, she'll just ask over and over and over and over and over and over and over again until finally it makes it through to me, and then I hear what she said and I give her some kind of answer, some kind of response. My daughter, my youngest daughter, is just like a Wi-Fi device in that she will retransmit her data over and over and over and over again until I give her some kind of acknowledgement. So if you've ever had kids, or if you've ever been around kids, or maybe if you've just seen some kids from a distance, you know that kids are a lot like Wi-Fi devices in this way. Devices will continually retransmit until they get their data through, until they receive an acknowledgement. We're going to come back to this concept a lot more later on in this webinar. So what happens when we have more than one Wi-Fi device on a channel? We know that it's never just one access point and one client device. It's usually several access points and lots of client devices. In fact, we can get up to hundreds of client devices on a channel. What happens then? Well, the rules still apply. Only one device can talk on a channel at a time. For example, if we have an Android phone that's transmitting some data to this access point, all of these other devices on this channel, including the access point, have to be quiet and wait for their turn to talk. This includes neighboring networks as well, or even access points that are part of your own network. If they're on the same channel and if they're within range, they're going to have to be quiet and wait for that turn to talk. This is known as co-channel interference, and this can absolutely, this is one of the major things that impacts the performance of a wireless network. We also have to think about data rates as well. In Wi-Fi, data rates are constantly changing. Devices are constantly switching which data rates they're using to transmit based on some measurements like how many retries they've had, how well they're able to hear the device that they're trying to transmit to. They all handle it a little bit differently, but what stays the same in Wi-Fi is that they constantly switch from a set of data rates. They constantly adjust their data rates. For example, let's say that we've got this Android phone is relatively close to the access point, so its signal strength is pretty good. So it's able to maintain a nice fast data rate like 54 megabits per second. It's a nice quick conversation. Whereas this device, this other Android device, is on the very fringe of the coverage area. So it's had to slow down all the way to a very, very slow data rate, like 1 megabit per second. That's the slowest data rate that we have available in Wi-Fi. It's also the most robust. It can fly very, very far because it's very slow, it's very easy to understand, whereas a faster data rate like 54 megabits per second is a lot more complicated, so it just doesn't go as far. It's not, you can't understand it from a further distance. The problem with this is that these two devices, if they're transmitting the same amount of data, they're going to use different amounts of time on the channel. For example, this 54 megabit per second, this device that's transmitting at 54 megabits per second, it's going to transmit and get off the air relatively quickly. It's not going to spend a whole lot of time on the channel, whereas this 1 megabit device is going to transmit 54 times slower. It's going to take it 54 times longer to transmit the same amount of data. This device is kind of like the slow kid in the back of the classroom. You know who I'm talking about? That guy, the slow kid in the back of the classroom? That one guy that every time he raises his hand to ask a question, you put your hand on your forehead and you just go, oh, great, here we go again. He goes, yeah, teach? Yeah, I had a question. Does that drive you crazy? It brings the entire class to a halt. That's exactly what happens when devices have to fall back to slow data rates. They become the slow kid in the classroom, and they put everything on hold until they're done transmitting. So we have to think about speed as well when we think about the half-duplex nature of Wi-Fi. We have to think of a lot of different things, and speed is definitely a prime consideration. Now, there's 3 types of interference in Wi-Fi. We've been talking about co-channel interference. Co-channel interference occurs when clients and access points on the same channel have to compete for opportunities to talk. They literally have to compete for opportunities to talk. And we'll get into the nitty-gritty of exactly how that works a little bit later on in this webinar. Adjacent channel interference occurs when wireless networks and their connected devices are on partially overlapping channels. So let's say we have a network on channel 5 and a network on channel 6 and a network on channel 7. They've each got a bunch of devices associated to them. The problem is that instead of politely taking turns talking or competing for airtime like we do with co-channel interference, with adjacent channel interference, these networks are just going to yell and scream over each other. They're going to constantly interrupt each other. They're not going to coordinate at all, which is going to cause retransmissions, which is going to cause more airtime usage and cause data rates to drop. Adjacent channel interference is bad. It's really bad, and we want to avoid it at all costs. In the 2.4 gigahertz band, it's really easy to avoid. Only use channels 1, 6, and 11, the golden rule of Wi-Fi. Next is non-Wi-Fi interference. You have to watch out for that. Non-Wi-Fi interference comes from non-Wi-Fi devices like cordless phones, wireless video cameras, baby monitors, microwave ovens. The list of non-Wi-Fi devices that have to use the same frequency space as Wi-Fi goes on and on and on. And the problem is that these devices don't have the same politeness mechanisms built in that Wi-Fi does. They just typically show up on a channel and just start talking. They just show up on a channel and immediately begin to transmit. And they don't coordinate with devices at all. They just spew garbage onto the channel. And when that happens, our Wi-Fi devices are basically going to have to back off and continually be quiet and wait for their turn to talk. Only one device can talk on a channel at a time, and that's true for non-Wi-Fi devices as well. Now, what we're going to talk about today, packet analysis, is really best for troubleshooting co-channel interference. It's really best for looking at the specifics about what is happening on the channel. It shows you the details about 802.11 congestion on a specific channel. It allows you to capture all the traffic that's occurring between devices on a channel, so you can look and see exactly what is happening on that channel. I always like to start my wireless troubleshooting with the physical layer. Now, if you were troubleshooting Ethernet, let's say that you had a desktop computer that was normally connected to a switch via Ethernet, and the machine was showing that there was no connectivity to the switch. Well, one of the first things you might do is you might check on layer 1. In this case, in the case of an Ethernet cable, layer 1 is the physical copper between the machine and the switch. So you might either test the cable with an Ethernet cable tester, or you might just replace the cable. You might just swap it out for a different cable to see if that fixes the problem. I like to do the same thing in wireless. I like to start with the physical layer. But in this case, the physical layer isn't copper. The physical layer is basically the spectrum. It's the air. And so I always like to start with spectrum analysis, and I use that to guide me to the next troubleshooting step. This is I'm typically going to see one of these two things on a spectrum analyzer. If this is a layer 1 issue, then I'll see a non-Wi-Fi signature. I might see this signature like this. This is a cordless phone, and that's going to basically jam channel 11. Channel 11 in this screenshot is basically done. Nothing is going to be able to work on channel 11. So in that case, I'm going to use spectrum analysis to identify and remove the non-Wi-Fi interference. However, if I see a signature like this, well, this is a Wi-Fi signature. This is basically Wi-Fi with very, very heavy utilization. The channel is very, very busy in this case. So that's when I'm going to go ahead and move to a different tool. I'm going to move to packet analysis at layer 2 to dig deeper into that Wi-Fi congestion to see if I can figure out what's going on, to see if I can figure out what the problem might be. So here are the differences between spectrum analysis and packet analysis. Spectrum analysis happens at layer 1, and it shows you the sum of all of the activity, all of the radio activity on that channel. So we're basically looking at the raw radio frequency activity. And one nice measurement that we get out of that is we get utilization out of that. We can see as a percentage how often that channel is being used. We can see how busy that channel is. Packet analysis happens at layer 2, and in this case, instead of just looking at the raw radio frequency activity, we're going to actually look at the data that's being passed between wireless stations on that channel. It's going to show us the details about all of the 802.11 congestion, all of the Wi-Fi congestion on that channel. We're going to basically be able to look at those conversations between devices to figure out exactly what's going on. Now, before we dive into packet analysis, there's a few things that we need to do. We've covered the basics about how adjacent channel interference, or I'm sorry, co-channel interference is caused by the half-duplex nature of Wi-Fi. And the next thing that we need to do is we need to look at the different types of frames that wireless stations will pass between each other on a wireless network. Now, in IPA, each frame gets a unique color, which is really nice because it's very easy to tell what type of frame that we're looking at just by color. So I'm going to color code everything from here on out. Now, the three main frame types are management frames, control frames, and data frames. Now, if you forget which is which, when we start to look at all the specific types of frames, if you forget which is which, IPA's got a really cool cheat sheet built into the filters bar. This is a drop down out of the filters bar in IPA, and you can look at, you can remember which frame type corresponds to which color just by looking at that cheat sheet. It's a really nice thing to have built into the tool. So let's take a look at management frames first. Management frames basically manage stations that are joining and leaving wireless networks. These frames help stations get on a network and get off a network. Now let's go through each of the subframe types and take a look at what types of frames are management frames. The first is a beacon. Beacons exist to basically access or basically announce that an access point exists. So for example, if I have my access point at home and it's called Joel's Network, it's going to, every 104 milliseconds or so, it's going to transmit a beacon to say that it's there. It's going to say, hey, I'm Joel's Network. I'm here. I support these data rates. I support this type of encryption. You can connect to me. And then 104 milliseconds later, it'll do it again. Hey, I'm Joel's Network. I support these data rates. I support this type of encryption. You can connect to me. Whenever you get your phone out of your pocket to connect to a new wireless network and it gives you a list of available networks, your phone knows about all those because of beacons. It's listening for those beacons, and it can show you which networks are nearby. The next type of subframe in the management frame type is a probe. Probes come in two flavors, a probe request or a probe response. When you connect to a wireless network, your phone or your laptop or your tablet or whatever you have keeps a list of all the networks that it's connected to. Each one of those networks that you've connected to is put in a profile. So for example, my phone has connected to a couple of example networks would be Joel's Network at home. That's the name of my network at home, and then also MetaGeek, which is the name of our wireless network here at MetaGeek. Whenever I leave home in the morning and I jump in my car and I drive down the street and away from my wireless network, my phone is going to start probing for familiar networks. It'll say, hey, Joel's Network, are you there? Hey, MetaGeek, are you there? And it'll just go down the list and it'll continually probe for familiar wireless networks. So that's a probe response, or a probe request rather. A probe response is when I'm riding up the elevator to come up to the office here at MetaGeek, and my phone says, hey, MetaGeek, are you there? In a probe request. And then MetaGeek responds in a probe response and says, yes, I'm MetaGeek, I'm here. And then they go ahead and get they go ahead and start connecting to each other. Now, probe requests and probe responses aren't required to get connected to a network, but they speed things up a little bit because it allows your Wi-Fi device to proactively look for familiar networks. It's always looking for a familiar network to connect to. But of course, we can always connect by just listening for beacons and connecting to a new network as well. That works just fine. It's just a little bit slower. Next are authentication frames. These are kind of funny because when we join a wireless network, we exchange authentication frames. But this is kind of a legacy item. This goes back to WEP, the original encryption method for Wi-Fi, back before it was even called Wi-Fi. The authentication frames were part of how we decided basically whether an access point would allow you to join a network or not. These days, we actually push the authentication part. Since we're using WPA and WPA2 now, we actually do that step later. So the authentication frames now today are just open authentication frames. They don't actually do anything. It's just a quick exchange that we do. It's just part of the legacy of Wi-Fi. Finally, our association frames. This is where a client device will say, hey, can I associate to the network? And the access point will say, yeah, you can associate to the network. So they'll do an association request and association response as they join the network. The next type of frame is a control frame. Now, control frames Whoops, my slide got a little messed up right there. I'll have to go in and fix that. Control frames basically control the RF medium, and they make sure that other types of frames get delivered. They make sure that all the other frames in Wi-Fi get delivered. The first and the most common is an ACK, which is short for an acknowledgement. Now, you're familiar with this already because we talked about it earlier in the webinar. Every time we transmit data, we have to reply with an acknowledgement. It's just like a TCP/IP ACK that happens in other layers of networking. The next type of acknowledgement is a block acknowledgement. Now, normal acknowledgements take a lot of time. Let's say that you're just streaming Netflix to a device. You have to go data, acknowledgement, data, acknowledgement, data, acknowledgement. It takes a long time. Block acknowledgements allow us to acknowledge a large block of frames all at the same time. So now instead of going data, acknowledgement, data, acknowledgement, data, acknowledgement, we can go data, 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 acknowledgement. We can acknowledge a block of data frames all at the same time, and that saves time on the air. Now the next type, this one we have to explain a little bit more in depth, is request to send and clear to send, or RTS-CTS for short. RTS-CTS helps us avoid hidden node problems. Basically, the way that this works is that if we have an access point that can hear two client devices, then the access point is going to know when it needs to be quiet and let other devices talk. But what if those two client devices can't hear each other? If those two client devices can't hear each other, then they might talk over each other, and then the access point isn't going to be able to understand them because they both talked at the same time. To really explain this, I think it's time to draw some stick figures. I'm going to draw some stick figures on the screen here to help you understand exactly what happens with a hidden node problem. So back at our old office, this is an office that we moved out of in about 2013, 2014 here at MetaGeek. We had a little kitchen. We've got a kitchen here too, but we had a kitchen with like a fridge, and there was a countertop, and there was a sink and stuff there. And that's where all the coffee, all the snacks and things like that are stored. MetaGeek keeps us well supplied with coffee and snacks and things, which is really nice of them. And so I was standing in the doorway between these two rooms. So there's an awesome stick figure of me. And then out here sitting at his desk was our IT guy, Rich. So Rich was sitting out here at his desk, and then Lael was in here. She was getting something out of the fridge, or she was warming up lunch, or something like that. Now, I could see both of them, but Rich and Lael, they couldn't see each other. All of a sudden, they both asked me a question at the exact same time. When they asked me that question at the same time, they were both talking at the exact same time because they didn't realize that somebody else was already talking to me. That's a hidden node problem. All you'd have to do is turn me into an access point. Please don't do that. But you turn me into an access point, and then they will both be client devices, and bam, that's a hidden node problem in Wi-Fi. RTS-CTS helps us avoid those problems. If we'd been using RTS-CTS in that human conversation, then Rich would have said, "Hey, Joel, can I ask you a question?" And I would have said, "Yeah, Rich, what's your question?" And that would have signaled to Lael that I was already engaged in conversation, and they wouldn't have both tried to talk to me at the exact same time. So that's an example of a hidden node problem. Excuse me. Whew, sorry about that. Battling a cold and a sore throat here, as you may have been able to tell. Head's a little fuzzy because I'm all hyped up on NyQuil, or on DayQuil too, so had to mute for a second and get a drink of water. Sorry about that. But RTS-CTS helps us avoid those problems. So let's move on to the last one, data frames. This is the whole reason why we have a wireless network. This is the whole reason that we have a network at all. Data frames carry higher level protocol data. They basically move the data around on the network. Now the funny thing about all these different types of frames that we've looked at, data frames are the only ones that make it onto the wired side of the network. They're the only ones that get through the access point. Everything else gets discarded at the access point. This is the actual reason why we have a wireless network, is to move these data frames. There's three main types. Of course, there's data frames, which are, they're just a data frame, and then there's quality of service data frames. These have quality of service numbers attached to them. So basically, we can prioritize certain traffic over other types of traffic. For example, we could prioritize a voice over IP call over somebody browsing Facebook. For example, the packets that are carrying my voice to you right now with GoToMeeting should have a voice over IP classification attached to them, so that way they would get priority on networks as they traverse all the various networks that they need to get from me to you. The last is a null data frame. These are kind of funny because they're not actually a data frame at all. These are more for things like power safe polls. They're a null data frame because they're not actually a data frame. I just don't think that that the people that came up with these standards had anywhere else to put them, and so they ended up getting stuck in this category. They don't carry actual data, but they are classified as a data frame nonetheless. So the next thing I want to talk about is how devices decide who gets to talk next. Now that we've covered the half-duplex nature of Wi-Fi, we understand co-channel interference, and we know about all the different types of frames that will be transmitted across the wireless network, let's talk about how devices arbitrate for airtime. How do they figure out who gets to talk next? So what we've got here is we've got a bunch of wireless stations. Now, a station can be an access point or a client device. It doesn't really matter. We've got station 1, station 2, station 3, 4, 5, and 6. And then we've got time moving from left to right here. So let's take a look at what all these devices, they're all on the same channel, how they decided who got to talk next in this scenario. So station number 6 is just finishing up sending some data, and there's a little bit of a break before when station 5 transmits its frame. This is called a SIFS, or a short interframe spacing. So now station 5, since it received and understood its data, it's going to reply with an acknowledgement. And so now what we get is we get a little break here. There's a little break in time where nothing happens. Basically, a diffs tells everybody that hey, there is a slice of time here. You guys can take the opportunity to try to transmit next. So station 4 has some data to transmit, and station 2 has some data to transmit, and they both hear this little break, and they go, oh, there's a chance here. We can maybe I can get an opportunity to talk on the channel. The next thing that they're going to do is they're each going to roll the dice. Station 4 is going to roll 9 slots, and Station 2 is going to roll 7 slots. Now what they're going to do is they're each going to very quietly, in their own head, they're going to count that number of slots. And if they count, for example, if Station 4 counts off 9 back-off slots, if it counts to 9 and nothing starts talking, it's going to start talking. It's going to say, hey, I counted to 9, nothing started to talk, so it's my turn to talk. Station 2, on the other hand, is going to count to 7. It's going to count all the way up to 7, and if nothing starts talking before it's done counting to 7, then it'll say, hey, nothing started talking, so I can go ahead and use this opportunity to talk. Now, of course, if they both start counting in their own heads at the exact same time, Station 4 is going to try to count up all the way to 9, and it's not going to get there because Station 2 only needs to count up to 7. So it'll count to 7, 1, 2, 3, 4, 5, 6, 7, and say, hey, nothing talked. It must be my turn to talk. So now it's going to transmit a request to send. That's going to signal to Station 4, oh, you didn't get your chance to talk. You had to count up to 9, but you didn't get there. But it's going to keep its remaining back-off counters. So it counted up to 7. It got interrupted. It only has 2 back-off slots remaining, so it's going to hang on to that number, but it's going to defer because it heard that request to send. Now, Station 1 rather, is going to transmit a clear to send. And so in this case, we're using request to send and clear to send. Station 2 said, hey, can I send? Station 1 says, yes, you can send. And when it did that, it signaled to everyone else on that channel, hey, everybody, I just gave Station 2 permission to send, and it's going to use the channel, so everybody needs to be quiet. When it does that, it transmits a nav timer. Basically, it's called a nav timer or a network allocation vector. It basically says, hey guys, everybody synchronize your watches right now and shut up for this amount of time. So every station that heard that clear to send knows, oh, they're going to take this long to talk, so I need to be quiet until they're done talking. So now Station 2 is going to transmit its data. That's the actual payload, the actual data that we're trying to transmit. Of course, we have a short interframe spacing. And then Station 1 gives its acknowledgement, and we're done. We have used up all of our time, and so that conversation is now done. We have now completed that conversation. So now, remember how Station 4 didn't get its opportunity to transmit? Well, it went from 9 slots and counted up and counted down, but it had 2 slots remaining. So now, once it hears that little gap, it's going to go, oh, hey, there's another opportunity to talk here. And at this time, instead of rolling the dice, it's just going to use 2 slots. So it only has to count to 2. Meanwhile, Station 2 has more data to transmit, and it has to roll the dice again. It has to start over from scratch. It got its chance to talk, and now it has to start over. This time, it's going to roll a 10. Which one's going to win? Station 4 is going to count to 2 and go, hey, nothing started talking, and it's going to transmit its data. Now remember, Station 4 isn't using RTS CTS with Station 3, and so it doesn't have to transmit a request to send. It gets to just go ahead and send its data. And when it does that, that alerts Station 2, hey, you can't talk yet, you have to defer, and then they all set their nav timers because they all know that they need to back off for that certain amount of time. Then Station 3 transmits its acknowledgement, and we're done. We've now had 2 separate devices transmit their data. 2 devices have arbitrated for airtime, and that's how it works. And the first time I heard this, I was just kind of amazed that Wi-Fi works at all. I mean, this is happening literally millions of times a second. If you've got your phone on and if Wi-Fi is on in your pocket right now, it's doing this. It's constantly arbitrating for airtime with all the other devices on the same channel. It constantly has to fight for that opportunity to talk. So how do we visualize all this? Well, go to a tool that's been around for a long time, and it's really an excellent tool. It's free. If you don't have it, go get it and learn how to use it because it's a very good tool, is Wireshark. Wireshark is a free and open source packet analysis tool, but it's a little bit difficult to visualize airtime with it. It basically takes all the packets and just lists them from first to last in the recording. So you just get this giant list of packets. The problem with that is it's really hard to tell who talked fast and who talked slow and who repeated themselves all the time, had to retry over and over and over again, who's eating up airtime, who's not using airtime. It's very, very difficult to visualize what is happening in this on a channel with Wireshark. And that's where IEPA comes in. With IEPA, we sat down and we thought, you know what? What if we could visualize packet analysis somehow? And that's when we came up with these multi-layered pie charts. With these multi-layered pie charts, we're able to stack up information in layers to show the total amount of airtime that was used. So this entire chart, all the way around this chart, represents the total amount of airtime that was used on the channel during the wireless packet capture. Then we break it down into layers. The innermost layer, the innermost ring in the pie chart, represents, in this case, our wireless network. So basically everything right here was all part of this network, Bronco Guest. We could see how many clients were part of that network. We can see that the retry rate was 59%. That means 59% of the time during this packet capture, devices on that channel repeated themselves, or rather on that network repeated themselves. If we move one more layer out, now we're looking at our individual access points. Now you can have multiple access points that are part of the same wireless network. In this case, we can see that this is an access point right here. There's a dividing line right there, and then there's an access point right here. There might be a couple more, but it's obscured by that pop-up window, and I just don't remember whether there are more access points or not. You go one more layer out, and now we're looking at individual client devices. So this is a client device right here. This is a client device right here, and then we've got some client devices that hardly used any airtime at all. They used very, very small amounts of airtime. You can see how we're moving out through the layers of the pie chart. When you get to the outermost layer, the outermost ring shows us our frame type. What type of frame did we transmit? If it's blue, that means that it's actual data. If it's purple or orange, that means it's just management overhead. It's not actual data that we're transmitting across the network. Orange is all of our control frames, purple are our management frames, and then blue are our data frames. So you can very quickly see what is management overhead and what is actual data that's being transmitted. IPA has some really, really great features that I want to show you. One of my favorites is that it shows you top talkers. It can help you identify devices that are having slow and inefficient conversations, and you can see which devices are transmitting the most data. It can also help you identify problem devices. It can help you pinpoint slowed conversations that are consuming all of your airtime, and it'll also automatically point out devices that are repeating themselves. It'll actually call those devices out. It'll give you expert tips so you can automatically see which clients have excessive retries, and it can help you identify network settings that can hurt performance. And one of my favorite features about it is that it will export to Wireshark, turning IPA into a really powerful filtering tool. So with that, I'd like to go ahead and switch over to a live demo. Let's go take a look at something live in our environment right now. Okay, so we've got IPA up and running here. I'm going to go ahead and connect an AirPCAP NX. That's a product by Riverbed that allows us to get full packet captures in Windows. Now, IPA is pretty great about accepting just about any packet capture that you throw at it, as long as your packet capture it contains either radio tap headers or PPI common headers. It's going to be able to open up that packet capture. So what I'm going to do now is I'm going to select channel 6 here. I'm going to select channel 6, and I'm going to start a packet capture on this channel. So now we're capturing everything that's happening on that channel. Next, I've got my old, trusty old Android tablet here. This is a nice 2012 Nexus 7. Pretty old now, but it's a great little tablet. And I'm going to run a throughput test from a tablet to the access point and to a machine on our local network here. So what you'll notice here is that our file size just jumped up big time. We just went from grabbing a couple megabytes every few seconds or so to now we're getting several megabytes per second of data. You can see that we've got about 90,000 packets. We're going to hit 100,000 packets here pretty soon. And as soon as the throughput test is done, you'll see that slow down pretty significantly. So we'll let that finish running. I'm going to let that throughput test run for 30 seconds, and now it's done. Notice that the file size just basically stopped. It's just now just moving along pretty slowly, and we're not getting thousands and thousands of packets like we were. That's because the throughput test is done. So I'm going to hit stop, and IPA is going to calculate all those packets that it saw. It's going to see what took up airtime, what repeated itself. It's going to do all the heavy lifting right away, so that way we can navigate through our packet capture really, really quickly as we use the tool. So let's let it finish processing its packets. And there we go. We got some data. Okay, so let's take a look at what happened on this channel. Now, these graphs, we talked about the multi-layered pie charts earlier. This represents all of the airtime that was used throughout the packet capture. So if we look, we can see that this network, MetaGeek, pretty obvious who that is, consumed about 3/4 of the airtime on the channel. If we go one more layer out, we can see that there's an access point called Cafe. You can give access points unique names in all MetaGeek products, and it all kind of all works together. It's really nice. This access point was responsible for basically all the traffic on this channel that belonged to MetaGeek. You go another layer out, and now we're looking at this ASUS device. Well, this 2012 Nexus 7 that I have is manufactured by ASUS, so that makes sense. That is my ASUS device that I ran my my packet capture with. And we can see that it spent most of its time sending quality of service data frames. Good, that's really good. We did see some block acknowledgments, that's good as well as some RTS, CTS. So there must be some hidden node problems. The access point must have decided to implement RTS, CTS at some point on this channel. Now up above, this view at the top shows a signal strength, or I'm sorry, not signal strength, but rather airtime usage over time. As you can see, when we first started out here, we really weren't using a whole lot of airtime. It was just kind of humming along right here at about 5–10%, something like that. And then this is the point where we started our packet capture. I'm sorry, not our packet capture, but rather our throughput test. You can hear the NyQuil really getting to me. That we can see that we hit almost 100% airtime usage throughout this packet capture, and then this is when the throughput test ended and things just kind of went back to normal. So you can see exactly what happened during that packet capture. So what I'm going to do now is let's take a look at what kind of data rates that we used. We can see that our retry rate was about 16%. So 16% of the time we repeated ourselves. Not bad, that's pretty good. I usually don't get worried about retry rates until I see about 25 or 30% or more. 57% of the time we hit 24 megabits per second. That's pretty good. We did a pretty good, we were using pretty nice fast data rates. And 24% of the time we hit 65 megabits per second, which makes sense because that's the fastest data rate that this Nexus 7 will support on a 20 megahertz wide channel in the 2.4 gigahertz band. So what I want to do now is let's drill down into this a little bit more. So I can click on the cafe here to drill down into that. The green up here in the top in the airtime over time graph shows us what our active selection basically it ties our active selection to that airtime graph. So this for everything that we did on the cafe, this is all data, this is all airtime usage that the cafe was responsible for. We can drill down even further. I can click on this ASUS device to drill down into it even further. So now all this green, this is all data that was caused by this client and access point conversation. The gray stuff here on the ends, like this stuff earlier, the tablet was not responsible for that. The access point was not responsible for that. It was only responsible for all this activity that happened in the center. Now, when we drill down into something, we can go over to the packets view, and we can actually look at the packets going back and forth. This is kind of a view that you would expect to see in Wireshark. So if I hit the center arrow to go all the way back out, we are now looking at, these are all the packets that we captured on the entire channel. This is everything. But as we start to drill down into this, like if we click on the cafe, now we're only looking at conversations between the cafe and its client devices. If we click on the ASUS device, now we've drilled down even further. Now we're just looking at that conversation between our ASUS device and our access point. Now there's one other packet capture I want to show you. This is a sample capture that's actually included in IPA. It'll actually show up right here. I've got to go find it because I've opened up a bunch of other packet captures. I'm always opening up packet captures, but these will be included. If you get the trial version of IPA, you'll see these right here under the recently opened files. We pre-populated with that. This is kind of a fun packet capture. We were at a trade show, and if you've ever been at a trade show, you know that the Wi-Fi there will kind of suck, right? It's a very, very bad place for Wi-Fi. But there was a vendor there that was streaming video to 100 iPads at the same time on a trade show floor. We thought that was pretty rad, so we got a packet capture to figure out how they were doing it, what was going on. So this is what we found. On this channel, we captured on, this is channel 52, so this is up in the 5 gigahertz band. We captured on this channel, and we saw an access point called iPad Demo 6. Now, there are a couple of other networks here. Voice WLAN 2 was there, but they used a tiny, tiny amount of airtime. And then there was one more, HP Blogger N was there as well. And I think there were a couple miscellaneous ones, but they were so quiet, they were so infrequent talkers that we couldn't even display them here. So they just get put in a miscellaneous slice of the pie chart. So then the iPad Demo 6 only had one access point radio on this channel. That's good. So they only had one access point here. That's great. And then we can see that there were a bunch of Apple devices. I'm going to assume that's probably the iPads, right? So they were streaming video to a few iPads on this channel. So they didn't have all 100 iPads on the same channel. They had all their iPads split up between a bunch of different channels. So now, if we click on this Apple device, we can drill down into it, and we can see that this Apple device buffered its video here and here. It didn't talk for the rest of the time. If we back out and go click on a different iPad, we can see that this iPad buffered its video here and here. If we back out again, we can see that this iPad buffered its video here. So that's another part of how they were able to do this, is they were able to get the iPads to all buffer video at separate times so they weren't stepping all over each other. And of course, if we want to, we can drill down into one of these and go click on the Packets tab and look at that exchange of packets. Now, the retry rate for this one was about 22%. It was fairly high. Not a great retry rate, but nevertheless, it did work. You can see the data going through, and then our acknowledgement, and then our RTS CTS. Now, one last thing I want to show you before we wrap it up is that IPA has powerful filtering tools built in. So, for example, if we only wanted to show the data for iPad Demo 6, I could just type in iPad Demo 6 and apply that as a filter. Now, we could accomplish the same thing by clicking on that layer of the pie chart, but this is just another way to do it. We can also filter down by client device, so I can select all the Apple devices. We can even filter down to a specific MAC address. So if there's a specific client device that's having trouble and you know its MAC address, we can go look at that specific MAC address. You can filter by frame type, subframe type. For example, we could pull all the beacons, probe requests, and probe responses out of this conversation. And once we've done all that, once we've applied the filters that we want, if we want a little bit more detail than what we get in IPA's packet view, we can simply hit hit File and hit Send to Wireshark, and that's going to take all those drill downs and filters that we have applied, and that's going to send them over here to Wireshark. So if you want to do deeper analysis, you can always take your packet captures to the next level, and you can bring them down to Wireshark for even deeper analysis. And if you're wondering what vendor was streaming video to 100 iPads concurrently, well, there's your answer right there. So so that's basically what I wanted to show you today for the live demo. For different options to get your packet captures, One way to do it is with the AirPCAP NX. This is a product by Riverbed, supports built directly into IPA. Another great way to do it is with Mac OS. If you have a Mac, like an old MacBook Air or MacBook Pro or something like that, you can actually get packet captures directly from within Mac OS with no additional hardware. Just consult our knowledge base for details on how to do that. And also you can get packet captures from other sources, like if you're savvy with the command line in Linux, or if you have an enterprise-grade access point that can generate a PCAP file for you, then those are alternative ways to get your packet captures into IPA. So at this time, I'd like to go ahead and turn it over to Julie to answer any questions that we might have.
Thank you very much, Joel, for that wonderful presentation. It looks like I do have some questions for you. I'm going to go ahead and get started here. Are there any licensing fees or restrictions on the equipment?
Not on the physical equipment itself. The AirPCAP is a one-time purchase. IPA is basically a license that you can buy. So you can just buy a license to use the software. It's just like any other software license out there. But the AirPCAP NX itself, no, it's just a one-time purchase.
Okay, thank you. With the IPA wireless frame types, are there any options to customize the colors, for example?
Not in IPA itself. You may have noticed that in Wireshark I was using my own color profile. In fact, if you look on your screen there, grab a notepad or maybe take a screenshot really quick, you can grab the Wireshark color profile that I've built. You can't change them in IPA, but if you'd like to, you can build custom color profiles in Wireshark. So maybe that's something you might want to check out.
Thank you very much. Next question. What is the turnaround time typically for a replacement unit? Would you happen to know?
I wouldn't happen to know. We're a small team here at MetaGeek, and we work pretty quickly. We also would work directly with Microcom on that to get a replacement to you as quickly as possible. I know that, like, for direct sales, like if a Y-Spy fails, in the rare event that a Y-Spy was to fail or something like that, we usually would just cross-ship you one to get you back up and running as quickly as possible. The AirPCAP NX, being a third-party product, might be a little bit slower because of that, but we'll work as quickly as we can.
Thank you very much. Next question. Who can we ask or contact in case we have any questions about the IPA?
Two places you can go. First, you can contact Microcom. Microcom's going to be happy to help you with any questions that you might have. You can also contact our support team here at MetaGeek. You can reach them by opening up a support ticket on our website, or you can just simply shoot an email over to support@metageek.net. Again, that's support@metageek.net, and our knowledgeable support staff is always ready to help.
Thank you. In addition to asking for support via email, like you just mentioned, are there hours of operation maybe for over-the-phone support, for example?
Yeah, MetaGeek, we do provide some over-the-phone support. We mostly provide it as, to kind of help you get trained up on how to use the application. And so our operating hours are typically somewhere between about 9 a.m. and 5 p.m. Mountain Standard Time. It varies a little bit. We are, like I said, we are a pretty small company, and so sometimes our support team will be out for a meeting or something like that. But we're available on the phone most business hours.
Thank you, Joel, very much for answering those questions, and thank you to everyone for attending today. And if you have any further questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. And if you wish to view any of the products mentioned or shown today, please visit us at www.microcom.us. Please remember, this webinar presentation has been recorded, and we will upload it to the Microcom YouTube channel so you can view it again. Thank you, Joel. I appreciate your time today. We love the presentation, and everything went very well today. I appreciate everyone's time. Have a fantastic day.